So, morning everyone. Today I will continue talking about my work, stellar populations and ionized gas in central spheroidal galaxies. And I'll start by reminding you some things that I showed you in my last talk. So if you don't remember, here I present a table of coefficients for each quantity, age. Can you see my cursor?
Yes.
Okay. Metallicity, extinction, a power law, and equivalent width of H alpha for a sample of central galaxies. So these coefficients represents the best curve fit of the plots below here. And the plots show the relation between the quantity, represented by color, and the halo mass in vertical axis, and the galaxy mass or velocity dispersion in x-axis. So keep this page in mind. In my last talk, I also said about the physical process, the cooling flow and AGN feedback. ICM cooling flow is when the hot gas in cluster loses most of its pressure and thermal energy by emission of X-rays. And the result of this cooling causes intense star formation in the central region, which is not observed. And the feedback provides enough energy to prevent the gas from accumulating and cooling in the central regions of the cluster, distinguishing the formation of stars. So, based on the correlations found and in previous works, these two elements appear to contribute in the evolution of central galaxies. So to better understand the behavior of this process in function of the mass regimes studies, we built a model for the evolution of central galaxies. So in this model, the occurrence of an emission line in a spectra must be the result of the confrontation between the energy dissipation of the ICM by emission in X-rays and the mechanical power of the AGN. Thus, we introduce a parameter C given by ratio between the power of AGN and the internal energy of ICM. So we have this equation 1. We need to parameterize these properties by the ratio between the feedback from AGN and thermal energy from ICM. So from start, we have this equation here, where the beta means mean molecular weight of the ICM particles. F here means ICM fraction mass. MP here is proton mass, and M500 here means the mass contained within a radius in which the density of matter is 500 times the mean density of matter of the universe. And we made some approximations, like I described here, and we got the equation 2. So the thermal energy from ICM is proportional to halo mass in this exponent, 1.67. So we then assume that instant kinetic energy of AGN is scaled with the accretion rate of matter by the supermassive black hole with some constant efficient, epsilon here, so we have this equation here. So we need to define a parameterization for the black hole accretion rate. And a simple model can be used for this is the Bondi models. In this model, the feeding of the black hole occurs through the accretion of hot gas in the neighborhoods when the gravitational potential exceeds the thermal energy of the gas. So this kind of accretion makes the feedback be mainly in the form of jets, exactly what occurs in central galaxies. So in this regime, in this model, the accretion rate scale with the black hole mass in this way here. So the accretion rate is proportional to black hole mass squared. So we can write the instant kinetic energy in function of the black hole mass. To write PE with the global properties of the host galaxy, we use the relation of Cormindi and Ho, this relation here, so we can relate the black hole mass with the velocity dispersion. So we have this relation between the kinetic energy and the velocity dispersion. So replacing equation 2 and 3, 2 here, and 3 here. Oops. In equation 1, in this equation here, we have the equation 4. So in equation 4, we have expression of Xi as a function of both of the cluster mass and the velocity dispersion. So here we have the cluster mass and the velocity dispersion of the galaxy. So if the Xi is higher, the Hn power is predominant, reducing the cooling of the gas. The effect of this reduction in cooling in the equivalent width of H alpha should therefore occur in the form of the inverse of Xi divided by Lc, where Lc is the luminosity of the stellar continuum at the position of H alpha line. So by simplicity, let's assume that Lc is proportional to the luminosity of galaxy in band air, Lr. According to Nigosh-Netru, the absolute magnitude in air band is related to the velocity dispersion in elliptical galaxies in this way here. Log of sigma is about 0.2 absolute magnitude in air band. This implies that the LR obeys this relation here. So the ratio between the inverse of Xi and Lc can be expressed in this way here. So we finally, let's introduce a positive exponent gamma in such a way that equivalent width of H alpha can be expressed as this relation here. And then we have relation between equivalent width of H alpha and our global properties, the velocity dispersion here and the halo mass here.
Okay, 2 minutes.
Okay. So if our model is correct, we must find a value for this gamma that here, this gamma here, that when replacing the last equation, produce coefficients similar to those we measure in the table on page 3. So if our model is correct, we need to find a value for gamma that when we place in this equation here, we find these coefficients here for A, B, and C. Look for this equation and this one. So it's very similar, so we need to find some value for gamma that we can find the coefficients that we measure. So we found that with gamma about 0.073, the coefficients found become very similar to those observed in our stacks for equivalent width of H alpha and for extinction. So considering that are uncertainties both in the model and in the measurement of these parameters, we can conclude that, in fact, our scenario of evolution to centers for the properties of H alpha and extinction correspond to the model described above. So our conclusions are that using Bohn's accretion model, ionized gas emission and interstellar extinction in central galaxies appear to be governed by a ratio between the thermal energy of intercluster medium and the instantaneous power of AGN feedback. producing relations well-defined scale between the emission and the masses of halo and the galaxy. So thank you.
Thank you. Okay. Questions, perguntas?